So in this section of the board work section, I want to kind of talk about the idea of what an acid and what a base looks like in a chemical reaction. When we're talking about chemical reactions, especially with these acids and bases, we're usually looking at them as what we call equilibrium reactions. And equilibrium reactions go both ways. So equilibrium. And that means that you have basically a front direction and a back direction. And usually there's not a reactant and product side, but technically you do have one side and you have another. Now from a general scheme of the reactions we're dealing with acid and base, you're going to have some kind of scenario where you have your acid plus a base, and that's going to react, and then it's going to form some kind of acid plus some kind of base. But here's the catch. This gets a specific term. This is called a conjugate. So everything on this side will get conjugate title. And here's the way it works. In a chemical reaction, you're going to have something that you are going to have behave as an acid. And then on the back end, it's going to behave as a base from that side. Now on this side, you might have something that behaves as a base, and then on this side, it's going to act as an acid. Now, these are called conjugate acid-base pairs. And usually, if you recognize one, you can recognize the other. But it starts with first being able to recognize how they behave. Now, for the sake of us understanding how an acid is going to behave, what we're going to be looking for when we're looking at an acid is somehow going from this, imagine this is the before scene and this is the after scene, we're saying that along this way it's going to lose, or the way they word it, is donate a proton. And the proton is going to be this H group. And I'll put proton just so we know what we're talking about. So we're donating a proton as an acid. So you might not see that it's donating. You might notice that, hey, this one has an H group on this side, and on this side, that same compound seems like it's H deficient. Well, you know that in order to go from here to here, something had to happen to that H. And so it donated or gave it away. And that's how you know how to pinpoint this guy as your acid. Now, conversely, when we're looking at the behavior of our base, the guy usually starts with some kind of deficiency and somehow goes through the process where it gains an H group or a proton going from here to here. Now, because it goes from here to here, that's going to operate as our base. And so when we look at these relationships, one's always an acid and one's a base, and they always yield a conjugate acid and a conjugate base. And their strengths actually flip-flop amongst one another, where if this is a strong acid, this becomes a weak base. Conversely, if this is a weak base, this becomes a strong acid. So their role and their strengths as that behavior suggest kind of that reciprocal capability, if you will. So here, let's look at some basic examples when we're talking about conjugate acids and conjugate bases, because honestly, when we're talking about questions, especially multiple choice questions that come from this, is you might be given a chemical reaction and asked to identify the conjugate acid, or just identify the regular acid. Now, regular acid would be here, and your conjugate acid is here. And if you were choosing them, you would have to choose the correct one. So we're going to look at a few examples together. And so hopefully that'll help us drill down the behavior of what an acid and base is. And a lot of these definitions are stemming from the Bronson-Lowry definition of proton donor, proton acceptor. So we have this first setup, and in this first setup, we have a situation where you have HClO4, and it's reacting with H2O, and it's yielding H3O and ClO4. Now before we start, I don't want you to get in the habit of thinking that one thing is always an acid or one thing is always a base, because, for instance, an example like water, depending on what it's reacting with, water can act as either an acid or act as a base. So you don't want to get in the mindset of thinking like that. Now, some of these are going to be easier to identify than others, because if you're familiar with the list of certain acids, like sulfuric acid or hydrochloric acid, you'll be able to pinpoint that that's the behavior of your acid. Well, let's look at this one where we're not necessarily familiar, and let's see if we see a trend. Now, I know I'm guilty of having tunnel vision, but hopefully you can see that this compound and this compound look pretty similar. If you can, that's great, you're on the right track, because that's what I want you to see. Is I want you to see that this relationship between this guy and this guy is very close. They look very similar. The other thing I want you not to get in the habit of is thinking that just because I gave you an example where this is our acid, that your acid's always going to be on the left, because that's not true. Your acid can be on the right or it can be on the left. So keep that in mind. All right, so keeping that in mind, when I compare this compound to this compound, I see that the main difference is that this guy has kind of a little minus symbol somewhere up there, and that this one does not have an H. So if this represented our before scene on the left side, and this is our after scene, we're seeing that somehow this guy removed or lost its H group. Now, because this guy lost its H group, lost or donated H group or proton, we know that this compound here acts as our acid. It acts as our acid. We know that because it had an H group, and going to this side, it no longer had that H group. And so on this side here, this becomes your conjugate on this side. Now, conveniently, if you know this is an acid, that makes this guy automatically a base, and this is called a conjugate base. So see how they're conjugate pairs? You have HClO4, and then it becomes ClO4 minus. Now, if we have an acid, this makes the job of identifying the base a little bit easier, because you've already identified one. But if you look at the behavior, you see in the before thing, this has H2, which means there's 2 hydrogens and an oxygen, and this guy has H3, which means there's 3 hydrogens and an oxygen. And it goes from having 2 to 3. That means somewhere, or from here to here, it gained an H group, or a proton. Now, because going from the before to the after, this guy gains a hydrogen, that makes this guy a base. That makes this a base. Now, maybe you're wondering what these symbols mean. I'm going to tell you, AQ stands for aqueous, L stands for liquid, and if I had it, S would be solid, and G would be gas. Aqueous just means I took the material and it's definitely dissolved in some kind of water. This is pure water, and so anytime you have water, it's just liquid, and then the other ones are just means they're dissolved in some type of water. So that's how we identified our compound. So a question that could come from this would be, all right, you're given the following problem. How do you identify the conjugate base? Or what is the conjugate base? The conjugate base would be this guy. And I forgot to mention that because this is a base, this is going to be our conjugate, if I could spell it correctly, it's conjugate acid. All right? So we have those relationships. So let's look at another one. And I think in my lecture, if you actually listen to the presentation, one of these is a popular compound that I talk about. And so we'll get into that. Here you have your NH3 that reacts with H2O to yield NH4 plus and OH minus. So again, the main thing you want to do is track the H in the before scene and the after. How does the H compare? Well, if I'm looking at this one and this one, I'm seeing a difference of an H, and if I'm looking at this one, I'm seeing a difference of an H. This one has 2 H's and an O, and this one has 1 H and O. And so the H's are being moved, but now I have to identify how they're being moved. Well, let's look at it this way. This guy goes from having 3 H's to now having 4 H's. So if I'm looking at it, going from here to here, this guy somehow gains an H, or a proton. And so if you know that, you also know that, well, if that one's gaining, something had happened to this one. This one went through a process where it somehow lost an H group. So loses or donates an H or a proton in this case. So how do we look at this? Well, we know that when something donates an H, i.e. proton donor, that's going to equal an acid. And when we look at this guy, proton acceptor, we're looking at what's called a base. So what does that mean? That means that we have identified this compound as our base. This is our base. And in fact, this is a very common base that we talked about before, and it's actually a weak base technically, which means it doesn't completely ionize or hydrolyze, dissociate, that's ammonia. And then this is water, which I said can act as an acid or a base, but in this case, it's an acid. Now remember, I said in the other one, the water acted as a base. In this one, the water acts as an acid. And so we identified the base and the acid, and now we have to just identify their conjugates. Well, if this is a base, that makes the conjugate in this case automatically a conjugate acid, and it makes this one a conjugate base. So now we've identified the roles in this chemical reaction. So you have your acid and your base, your conjugate acid and your conjugate base. And it all is cited based on identifying what the H group is doing. So knowing that, let's look at one more for posterity and make sure we're on the same page. We have the problem HF reacts with HSO3, TOF minus H2SO3. So if I'm looking at this, I'm looking to see which one loses an H, which one gains an H. Or if I'm looking at this guy, HF goes and loses an H group. Loses an H group. So this one donates an H, or proton. So that's that guy. Now because it donates, that tells me that HF is an acid. And in fact, it is an acid. It's a weak acid, fluoric acid. So now, with this one, we have HSO3, and comparing that to this one, it goes through and it gains an H group. So that means this is a base. That means that this is a conjugate right here. This guy is a conjugate. And it's the conjugate of this acid, so that makes that a base. And then when you compare HSO3 minus to H2SO3, you're seeing that it becomes a conjugate acid. Now remember, I talked about this before, but this is called diprotic, and this is a monoprotic compound. And these equilibrium, or these double arrows, half arrows, mean that the reaction goes this way and it goes that way. And it's cool because if we rewrote the equation and flipped it on that side, this guy would still perform as an acid, this guy would still perform as a base. It just means that if the reaction was flipped, the conjugates would be on the right side of the equation, and that would be these guys, as opposed to these guys in this particular case. And so, hopefully we've tied together the relationship between acid and base, and we better understand this concept of conjugate acids and conjugate bases, and are able to identify them as they relate to equilibrium reactions. Because one of the hallmarks of being able to understand acids and bases is just their behavior in chemical reactions. And so you want to make sure you have kind of a home list of common acids that you're familiar with. Those include sulfuric acid, hydrochloric acid, phosphoric acid, to name a few. And with these particular acids, these are your common strong acids. They are strong acids. And here's the thing. With a strong acid, what makes it a strong acid is its ability to completely dissociate. And you see that word dissociate, and you're like, well, what does he mean by dissociate? Well, it means this. It means that if I took a compound like HCl, hydrochloric acid, and let's say I had fictitiously 10 molecules of it. Well, when that molecule breaks down and dissociates, you're going to end up with 10 of these. You'll end up with 10 molecules of hydrogen, and you'll end up with 10 molecules of chlorine. So 10 molecules of each. And so that means that 100% it breaks apart. Now, once it breaks apart, it then can go on and react and combine with another compound. But if it's a weak acid, you won't get that. What a weak acid does is, for instance, let's take a common weak acid, which is acetic acid. And let's say we have HC2H3O2. And what happens is this H group is going to dissociate. You have 10 molecules of this. Well, supposedly what happens is you might end up with a scenario where you get some of these H groups that break up, and you might get, I don't know, maybe 2 of them that break up here. Then you'll end up with this acetate ion here. You'll have 2 of those. But you know what? 8 of these guys, which aren't really written in the reaction, decide that I'd rather stay being this. So you end up with more of these than them actually breaking up. These can then go on and react, but this is not as efficient when you react. So what you end up needing is more of this to get the same job of this done, because these are considered weak and those are strong. Now bases kind of operate the same way, where they're willing to react with all of these, but if they're a weak base, they won't react. Most strong bases feature the whole OH hydroxide nomenclature as a part of them, and so that's usually a ringer for dealing with those kind of compounds. Now, one of the weak bases that we've seen, I guess, is ammonia. So you want to make sure you remember that, and that's a weak base. So when we're looking at the idea of acids and bases, hopefully you can identify them, and hopefully you better understand the relationship between what strong is and what weak is when referring to those compounds.